welcome Professor Giovanni. I believe that I have used correct word Giovanni.
Yeah, that's correct.
So I welcome on behalf of the physics department to this talk. And we are grateful that you accept our invitation for this talk. And let me introduce about the BITS Pilani and the physics department in Pilani campus to you. BITS Pilani is a deemed university, and it was established in 1964. And currently, we are offering 3 different type of programs, namely first degree, and then higher degree, and then PhD degree. So in the first degree, we offer this Bachelor of Engineering and Master of Science programs, Master of Science programs in physics, mathematics, chemistry, biology, and economics, and Bachelor of Engineering program in various engineering disciplines. And apart from this, we have higher degree program mainly for engineering, Master of Engineering. And in the PhD program, we offer the PhD program. For physics department, we are involved in the Master of Science in Physics program, the first level degree program, and a PhD program. And apart from that, we have also one certificate program that is minor in physics for the students, mainly students registered in engineering degree. But if they have the interest, they can explore physics through this minor program, in which they can register in 5 courses. Some of them are compulsory courses and some of them are elective courses. So they can earn this minor certificate in physics. And in the PhD program, we have, at present, we have 20 faculties in Pilani campus. So BITS Pilani has 5 campuses. One is in Pilani, that is, this is the oldest campus, the mother campus. And then we expanded to Dubai, and then Goa, and then Hyderabad, and recently in Mumbai, the School of Management. So we have 5 campuses. So in Pilani campus, we have 20 faculties, and the faculties work in different areas. So some of the faculties work in the early universe problems, and some of them work in nuclear and particle physics, astrophysics, and some of them work in atomic and molecular physics, like me, and some of them work in complex systems, and mainly the most major portion of the faculty work on condensed matter physics, both in experimental and theoretical physics. And presently we have around 30 PhD students. So that's all about from my side about BITS Pilani and the physics department in BITS Pilani campus. So I invite my friend Dr. Didier Sebiu to introduce speaker. Over to Didier.
Okay, thanks very much, Rakesh, and thanks very much, Gianni, for accepting this, give this talk. So Gianni, we've known each other for quite a long time. I don't remember exactly, but the first time I met you, that was probably decades ago in Frascati. At that time, I was visiting, I was spending 1 month every year to Frascati to work with my friend Rino Natoli. And then we had some closer contacts when one of your PhD students, Fabiana da Pieve, worked on the theoretical model of Auger photoelectron coincidence spectroscopy with me, and she spent 4 months in Rennes to implement the spectroscopy into the MSPEC code. And more recently, we've been involved in this preparation of a European proposal centered on plasmon, and this is where BITS Pilani comes into the play as well, because this proposal involves 3 people in BITS Pilani, so Rakesh Chobisa, who is more in charge of the plasmon in theoretical view on the plasmon in E2E spectroscopy. And then on the applicative side, there is Raj Kumar Gupta and Manjula Devi, who are working on using surface plasmon resonance for sensors directed towards medicine. So I think that's all on my side. Now, Gianni, I give you, it's your time to tell us about all these nice things that you have prepared.
Let me interrupt for a while. Yeah. So I request that we should mute ourselves, and let the speaker to present the whole presentation. And at the end, if you have any query, you can raise your hand and we can address those queries. Will it be okay, Stefani?
Yeah, it's okay with me. I will be pleased to answer as many questions at the end. Thanks.
Okay. Okay.
Well,
thank you.
First of all, I wish to greet good afternoon to everybody. And let me thank Rakesh for giving me this opportunity. I'm very excited of giving, I was telling him of giving this talk at such a distance. And let me thank Didier for the nice introduction. Now, let's see what should we discussing this afternoon. Well, first of all, it is now a century that quantum mechanics is around, has revolutionized the interpretation of the world around us and inside us. It has been used to explain properties of neutron stars, properties of metals, of DNA, and anti-cancer drug. And we do rely on quantum mechanics and on for many technical applications like electronics, magnetism, used for conservation of cultural heritages, and even for some tomography. Now, in spite of all these successes, you might ask if there are still, after a century, if still there are questions to be answered. Well, one nut that was hard to crack is how to deal with correlated motion of electrons. What does it mean? Well, even if we get a very simple atom like helium, and which is a nucleus plus 2 electrons getting around, and we want to describe it, well, we know that we can use this, write the Hamiltonian, solve the Schrödinger equation, and this will give us energies and wave functions. Well, all of this is simple, but there is a problem. The problem is that the Coulomb interaction between the two electrons make this equation, the Schrödinger equation, not exactly solvable. So you might say, well, we just forget about the energy correlation, but actually you can't, because this is exactly the term that determine fascinating properties, such as high temperature superconductivity, colossal magnetic resistance, and the magnetism itself, and all quantum size effect that nowadays are so much exploited. So let's have a brief overview of what has been done to deal with this problem. What the zero order approximation is to apply what we call the independent particle model. It means that we I have to go back. Yeah. We just deal with the central field of the nuclei, and we treat the electrons as if they were free in this Coulomb potential? Well, in this case, the wave function of the n particle is just the product of the wave function. But then we have to realize that those are identical particles and have a spin. And here it comes in play the Pauli principle, and we can take this into account, writing down as a Slater determinant the wave function. Now, properties of, but now we can realize that the properties of many particle system can be modeled only if the correlation is taken into account. By correlation, again, we intend the Coulomb interaction and the exchange interaction of the two electrons. Is this term relevant? Yes, it is, because if we just get 2 or 3 electron atoms, the contribution to the energy goes from few eV to tens of eV. So is substantial. So let's take, for instance, the Hamiltonian of the system, well, of the n-particle system. The Hamiltonian of the n-particle system, again, the terms of Coulomb interaction between electrons makes not exactly solvable the system of differential equation which is generated when we try to solve the Schrödinger equation. So which way around have been used? Well, what is still the best method used is the variational principle. By variational principle, it means we take the wave function of the system that gets the lower bound in the expectation energy. Once we've got this, we can determine all the observable of our system. In other terms, it means we can predict which are the properties of our system. Usually this is done through what are called the density matrices. I will remind you in a moment what those density matrices mean from a physical point of view, but we see that the expectation value of an observable is usually made up of a sum of a term which not depends on the motion of the electron, position of the nuclei, the one that's determined by the motion of the individual electron, and the third one, which is the motion of the correlated electrons. So you see, in whichever kind of property of matter we try to describe, we have to take into account this correlation of the energy. Now, which is the physical meaning of what we call the second order density matrix, what I've been writing with capital gamma? Well, the physical meaning, just forget about you can calculate, but you calculate it with suitable integration over the wave function. But what is relevant is that if we multiply this second order density matrix by the elementary volume dV1 and dV2, we obtain the probability that one electron stay in the volume dV1 at position R1 with Z1 as a spin, when all the other one of the other n-1 electrons are in the volume V2 with coordinate R2, Z2. From the second order density matrix can be derived the first order density matrix, which means the properties of the individual electron. And in turn, the meaning of this is the probability of finding one electron in the usual volume dV1 coordinate R1 spin Z1 when all the other electrons are in one of the all the other electrons is in the volume. What we have to notice is that for what concerns the second order density matrix, the probability vanishes when R1 is equal to R2. And we will see that this is going to be reflected in what? This is going to be reflected in something that was introduced by Slater in the 35. It is a way to take somehow into account correlation, and this is what is called the Coulomb Hole. What does it mean? That if you take, for instance, the helium atom and one electron of the helium atom, and then you plot the probability for finding a second electron around this one, you get a distribution like this one. So it means there is a dip of probability around the electron E2 in this case. Is a sort of no-fly zone around E2 for the other electron in the system. But we said that we don't have to forget that electrons are identical particles and have a spin. So we have to take into account also the interaction of the spin, and the interaction of the spin gives rise to what is called the Fermi hole. What does it mean? It means that if two electrons, say the electrons red, which is fixed here, and the other electron, which is distributed in the space, have the same spin, the probability for finding the second electron close to the first one has a minimum, whereas if they have opposite spin, has a maximum. So all of this complex behavior due to the correlation between the two electrons must be somehow modeled and put in our calculations in order to explain properties of matter. To make a long story short, we start from the early 30s of the past century, in which the old band theory was built up ignoring correlation. So it means that at the zero order, properties of matter can be described by ignoring correlation. But if we then go but already in the few coming years was realized that correlation are important to describe a transition metal oxide. They are relevant to describe the 3D electrons, and they become paramount relevance when the interaction energy that we call with the letter U from now on becomes on the same size of the bandwidth. Nowadays, what is the cornerstone for the quantum description of matter is what is called the Hohenberg, is due to Hohenberg and Kohn and Sham, and is the density functional theory. Now, the density function, apart from details of density functional theory, what we realize that even though in principle this is an exact solution, in practice, we have to use a functional for the total energy, which is strictly related to exchange correlation interaction. So again, we have to use some kind of model for exchange correlation interaction, even in the density functional theory. So in spite of the progress done, the problem of how to model and how to learn something about correlation of the electrons is still present and there. As we said, we resort to models whose objective is to restore the simplicity of the independent particle approach while keeping all the complexity of the many-body interaction. Now, something comes to our mind is, but all of these models are just mental abstraction, or are they experimentally verifiable effects? Well, this is going to be the core of my presentation, try to answer to this question. How do we do experimentally? Well, you have to realize that electron correlation are elusive to most of the say conventional spectroscopies. Why? Well, we have seen that the expectation value of the energy is made up by both the single particle and the two particle behavior of your system. And it can be shown that the single particle in conventional spectroscopy is the dominant part. So if we want, so how to get around this problem? Well, the idea how to get around was already in a paper by Einstein at the beginning of the past century, in which he was saying that, however, we will not exclude the possibility that that the electrons absorb only a part of the energy of the light quanta. This is in the context of photoemission. So what does it mean? That the photon coming in can strike out of the target not just one electron, but more than one electron. So the idea is, well, if we can try to strike out of the target two electrons, this is a clear correlated event that we are dealing with, that we might use this to try to have a tool which is sensitive mostly to the correlated behavior and shades down the single particle behavior of the system, which is the scheme of principle of an experiment like this. Well, you get a target that can be, it has been either an atom, a molecule, or a solid. From now on, I will be keeping as a field rouge the solid examples on solid, but you have to realize that we will be mostly focusing on correlated behavior of the electron. So everything is going to be easily translated to atoms as molecules as well. So one monochromatic photon comes on the target. As Einstein foreseen, two electrons are ejected, say in the two cones omega-1, omega-2. Then with two detectors, I can, with two analyzers, I can measure the energy and momentum. And what is important is that I record the events only when the two are coincident in time, which means I am sure that they are coming from the same ionization event. Oh, sorry. Now, you might argue, well, when this experiment that I will use the acronym one photon in, two electrons out started. Well, they started in the late 90s of the past century, whereas the photoemission, for instance, was already well developed at the beginning of the century and had an impetuous growth with the arrival of the synchrotron radiation. For instance, it has been used largely to determine binding energies. Now, why instead this other experiment came around in the 90s? Well, if you look at the cross sections, you see that the cross section here is for photoemission from a lithium atom. And then we get the probability, so the cross section for the photoemission of two electrons from the same lithium atoms. Well, here we have 10 to the minus 18 centimeters square. Here we have 10 to the minus 22. So it means that we lose 3 orders of magnitudes. Furthermore, the early coincidence spectrometer had the luminosity reduced by a factor 2 with respect to the conventional photoelectron spectrometer, which means that we had to wait for the availability of the third generation synchrotron radiation and mostly to the multi-detection and large throughput experimental setup in order to perform this kind of experiments, which are very demanding. Which are the two most common experiments performed? Well, the first one, which I call double photoemission, is the one in which electrons are removed from the valence band. So from the valence state, in this case, could be either a solid or an atom or a molecule. Photon comes in, doubly ionized target, and 2 electrons are ejected. In this case, as the 2 electrons are ejected in the same event, the excess energy between transition energy from the neutral to the double ion and energy of the photon is going to be shared between the 2 electrons. If the energy of the electron is large enough, of the photon is large enough, besides of the double photoemission, also D is allowed. So the photon comes in, creates a core hole, and if the core hole is long enough lived, this will eventually decay through an Auger process. So in the end, we will end up with a photoelectron and an Auger electron. But what I would like you to notice immediately is that the final double ion state that we leave behind is the same in the 2 processes. Now we will make use of this concept in the following. Again, photon comes in, 2 electrons are coming out in the DP event. I measure them in coincidence. I don't go in detail, but there are electronics that allows you to discriminate when these 2 electrons happen to be generated at the same time and when not. And what is interesting is that if I calculate this cross-section, the cross-section for a process like this, the matrix element is a 2-electron matrix element, which means that, for instance, in the helium atom, for instance, in the absence of correlation, the probability for this process is 0. So it's highly sensitive to correlation. What do we mean? Well, what do we measure? Sorry. We measure a cross-section which is differential, a 6-fold differential, a differential in the 2 solid angle we've mentioned it before, and in the energy of the 2 electrons. And this is characteristic of all this kind of 1 photon in, 2 electrons out experiments I've been describing. What about when we ionize a core hole? Well, we get the photoelectron. Eventually, the system decays, autoionized, generating the Auger electron. I measure in coincidence the 2. Now I have to take into account that there are selection rules that are working both in the photoemission and the Auger decay. If I apply these selection rules, what I immediately realize is that the line shape of the Auger that I measure is not a conventional line shape, is the line shape of an aligned ion, because through the photoelectron, I am selecting subsets of core states. We will come to this concept later on. And again, this will be shown, it's very sensitive to correlation. Also in this case, I am measuring a 6-fold differential cross-section. If everything went this way, we will say that this apex event was a 2-step event. Why I have to introduce this concept of 2-step and 1-step? Well, because I said that this description is correct if the lifetime of the ion of the core state is long enough. If the lifetime becomes comparable or shorter than the interaction time of the electron, the core hole state is not anymore a stationary state. It becomes an ill-defined state, is a sort of transient state through which the process is happening. And so the whole process becomes a one-step electron. So it means that I am generating the two final electrons, but going through a core hole intermediate state, which is not a stationary state, and so its spectrum can span over the whole spectrum of the system, including excitation states. What is important is how we represent this result, because as I said, we measure six-fold differential cross-section, so we are not able to represent this cross-section as a function of the six variables, but we can get subset of them. The three-time representation I will be using is the first one, which is in the function of the parallel momentum. What I can use is the projection of the momentum of the electrons onto the surface of the system. And here, in false color, will be represented the intensity of coincidence event, which are measured when one of the electrons is fixed, for instance, in this position. The other one is made to move over the whole domain, and we record the intensity of this. On the other hand, I can decide to plot the intensity of coincidences versus the energy of electron 1 and energy of the electron 2. So each point of the surface is going to tell me the probability of measuring, for instance, electron 1 at 40 V, electron 2 at 140. In here, for instance, you see immediately the maximal intensity you have at 145 and 135. The third way I can use this data is to project on only one of the energy. So I make constant the energy 1, I change the energy 2, which means to get cuts along these ways. And what we get is what I told you before, the Auger line shape for a very well-selected subset of core states. Which are the problems that I'm going to address? As I told, we want to know if the approximation that we have been doing are mental abstraction or can be experimentally observed. Well, the first that we will deal with is the exchange correlation hole. I mean, this exchange correlation hole is just a thought, or there is something real that we can measure. Then the correlation energy. Does the correlation energy depends on the spin state of the electron? The third one is we have said that the correlation energy is made by the Coulomb interaction, a part due to the Coulomb interaction and a part due to the interaction of spins. Can we disentangle these two terms? And finally, one of the effects of the correlation of the electron is the screening. When I create a hole, electrons are moving to screen the hole. On which time scale does it happen? So I will give you 4 examples through which I will try to answer these questions. Let's start, as I said, from the exchange correlation hole. So the exchange correlation hole here is made of a part which is due to the Coulomb interaction when the two spins are anti-parallel. And then if I add the part due to the interaction of the spin, I get a bigger, an increased hole. So the total exchange correlation hole has a shape like this. Now, this is a representation of the pair correlation function as a function of relative distance between the two electrons. So this one is what I called before a sort of no-fly zone around one of the electrons. But now we know that whenever we have a structure in the direct space, this feature is expected to be reflected in some kind of feature in the conjugate momentum space. And this is what we use in this experiment. What kind of experiment is this? This was performed at Bessie by the Halle group. And again, remember, is double photoemission. So a photon comes in, two electrons are coming out. The photon energy is low enough to be sure that we are not creating core holes. And again, what we measure are the two electrons. Now we can measure individually the electron 1 and the electron 2, and then the coincidence between the two electrons. If we plot as a function of the ejection angles, the distribution of electron 1 and electron 2, we see that this has this distribution as a maximum around normal to the surface, both for electron 1 and electron 2. But if I now fix electron 1 here and measure the distribution of the coincident electron 2, what I get is a minimum around E1 and maxima away from E1. If I project everything on the energy E2, I get, as I was saying before, this cut. And so you see, we get a dip in the probability of creating the electron pair, which is centered exactly when R1 is equal R2. Now, if we measure the breadth of this hole and we convert this from angle to momenta and then into the coordinate space, we get that this hole has the size of a few angstrom, which is exactly what the DFT model will be using to describe this copper. And to convince, what is really convincing that this hole is due to correlation between electron 1 and electron 2 is that if instead of performing this experiment, we move electron 1 in this position, then you see that the distribution skews down and the minimum moves together with electron 1. And if the electron 1 comes here, again, the minimum comes here. So, in conclusion, out of this kind of experiment, I think it has been demonstrated that the exchange correlation hole does exist, and we can experimentally measure the size of this hole. Let's move now instead to an apex experiment, which a photoelectron-Auger electron coincidence experiment. Here is a schematic of the apparatus that we've used in Trieste at Electra. And as I said, this is a multi-coincidence apparatus. It means that you can measure. See, the photon comes in, there are several electrons coming out, and they are individually measured by the individual analyzer, and I can afterward establish correlation between them. Why are we so interested in getting at the same time from the same target all these different kinematics? Again, to make a long story short, what you have to focus on is that the selection rules will tell us that according to the correlation that we make between the different analyzers, we can select final state of the system, which is either in a parallel spin condition or in an anti-parallel spin condition. To establish some kind of correlation between electron correlation and spin state, it's very relevant for what concern and for understanding the behavior of the magnetic system. Here is the result. The experiment was performed on an iron film. And what we are looking at the 3P photoemission. So this analyzer are looking to 3P photoelectrons, whereas this analyzer is looking to the M23 VV superconcentronic decay. And we measure the Auger line shape, which is reported here. This is the energy of the Auger electron, and here is the intensity. Again, here is the scheme of the reaction that we are dealing with. The dashed line shows what is measured by conventional Auger. So as you see, the conventional Auger of the system is pretty dull, and no much hope to get information about correlation. What happens if I distinguish between final ionic state with the anti-parallel spin and the parallel spin? Well, what we see immediately that for the anti-parallel and parallel spin, I have two completely different line shapes. Actually, I can, sorry, these are the two electrons. I can define a decreasm, a dichroic effect in this measurement. How do we interpret this? Well, we interpret this by the help of the Chini-Savasky model. This model tells us to take into account correlation in the Auger line shape. What we can do is to get the autoconvolution of the density of state of the system, one particle density of state, suitably convolute that, and take into account the correlation energy. Out of this, what do we get? What we get is that if the correlation energy is 0, we get what we call the band-like line shape, which is the black dashed line. And this is just the autoconvolution of the one particle density of state. Now, if we start increasing the correlation energy from 1 to 8, what you see is that the line shape gets skewed towards the lower energies till you reach a critical point beyond which the whole spectrum collapses in a single strong resonance, which is a resonance due to strong interaction between the two holes which are left in the ionic state. So, if this is true, as it has been demonstrated to be true, using the position of this that we call atomic-like Auger transition, we can try to infer the correlation energy, because the correlation energy is related to the distance in energy between the center of the band-like and the observed atomic-like. If we apply this to the measurements I have already shown you, what we see that starting from the single particle density of state, majority and minority, getting all the possible autoconvolution, majority with majority, minority with minority, majority with minority, and using the correlation for the up, 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 down spins, making a long story short, we see that all of the transition are more or less, at least within the energy resolution that was proper of this experiment, well accounted by the non-correlated line shape, which is this one. There is just the majority spin-up contribution, which is shifted by 2.7 electron volt with respect to this non-correlated Auger line shape. So it means that it is for the it is only for the majority spin electrons that they interact strongly and they exchange correlation energy is of the order of 2.7. So this is already a demonstration of sensitivity of the two holes in the majority to the correlation energy, and again the distance between the two peaks gives us a way to measure this correlation energy. But as I said, as it was introduced by Slater, this this correlation energy is made by a Coulomb part and a spin part. Can we disentangle these two parts? Well, this was done in a successive experiment done again at Electra, in which again we are working on iron. This was a two-layer of iron deposited on silver. And this system was chosen just because the interaction between upper film and substrate is very mild. And so this is the closest approximation that we can have experimentally to a freestanding iron film. And we have repeated very much the same experiment I have described before, but with improved energy resolution on this system. Again, here, this is the scale for the energy of the Auger electron. And here is again the shape of the conventional Auger. But when we move to angle resolved apex, I mean distinguishing the two configurations of anti-parallel and parallel spin, we get the red and the green spectra. And you see that there are quite large differences, and again, a large dichroic effect. How do we explain this? Well, we resort again to the Chini-Savasky model. But in this case, we notice that in the anti-parallel configuration, there are, if we distinguish individual contribution within the shape of the Auger spectrum, and this is the individual contribution was possible to be distinguished just on the basis of this different shape that we have in the anti-parallel spin and in the parallel spin, because we can associate this different configuration of the final ion with symmetry of the orbitals involved, and so we can make a one-to-one assignment of these peaks. And you see that there are the green peaks, which are more evident in the anti-parallel, while the red peaks are more evident in the parallel spin configuration. So now we use again the Chini-Savasky model to explain both the uncorrelated behavior, which is the dotted line in both spectra, and the correlated behavior, which are all the different contributions. These different contributions are this autoconvolution of the one particle density of state modified by different individual values of the correlation energies. This has been done using a fitting procedure that took into account both spectra at the same time. And in the end, we were able to build up a table in which the correlation energy is given, correlation energy as defined before as the distance between the uncorrelated spectrum and the correlated peak, as defined for each one of these individual peaks. These results are reported in this table, and for instance, the distance u, which is highlighted here, is relative to this final state. I remind you that in iron, the two dominant bands are the EG and T2G band. And so this means that this peak here corresponds to final state in which I have two holes in EG, both with majority spin. And then I can go so on and so forth for all the other. Now, what is interesting for me? What is interesting for me is that here, for instance, if I get two, I can select, for instance, final state in which I have T2G spin up, T2G spin down, and here T2G spin up, T2G spin up. So as you see, the electronic state is the same in the two. So I can expect that the Coulomb interaction between the electrons here and there would be the same. What is changed from here to there is changed the spin configuration. So the difference in energy that there is between these two transitions correspond to the spin flip energy, which in this case is 4.4 eV. But this transition, the T2G, T2G, has a correlation energy of 8.7 electron volt. So it means that the 4.3 electron volt which are left can be assigned to the Coulomb interaction. So for this Auger transition, we say that 4.4 EV are due to spin flip or to exchange, and the remaining 4.3 are due to Coulomb interaction. And this can be done for all the transition observed. So again, we confirm that the exchange correlation energy, it does depend on the electronic state of the electron considered, but it also does depend on the spin condition of this, and that we can disentangle and measure the contribution to the exchange correlation energy due to Coulomb and due to exchange. And this is something very important in order to model both the magnetic properties and transport properties in a solid. Let's now move to the last example that I would like to mention. The last example in the one in which we say that we want to we want to address the core relaxation time and core lifetime. Now, on which time scale happens the core screening, the core hole screening? Well, we saw that this happens on a femtosecond time scale. Now, ideally, what we would like to have is to have an experiment in which we can access the same ionic final state going through two different core hole states, one shallow, one deeper, that have pretty much different lifetimes. Why? Because, as I said at the beginning, in one case, long-lived core hole state, we expect to have a two-step model working. So if we plot probability of finding coincidences as a function of the two energy, E1, E2, we will find two narrow regions in which those coincidences are happening and zero, say, everywhere else. Whereas if the core hole state is short-lived, all the process will go through a resonance that is ill-defined for through a state which is ill-defined for what concerns energy. So the energy of the two final electrons is not anymore strictly correlated to the photoelectron event and to the Auger event, but is going to be evenly distributed between the two electrons. And so we expect a distribution of probability, which is something like this. So the first question is this true, is this behavior correct? Shall we actually to expect such a behavior? We have chosen silver as a sample. Why? Because for the 3D, we know that this is a short-lived, a core in 3D is a short-lived state, and indeed the photoelectron is a narrow peak, some 0.3 electron volt. Whereas if we photoionize the 4p is a short-lived one, and indeed we observe the photoelectron which is as wide as 13 eV. Well, the first thing that we observed is that what we expected is actually observed by the experiment. You see, in this case, the plot versus energy 1, energy 2 is isolated in 4 different islands. And we interpret this as the 3D 5.5 MVV or 3D 3.5 MVV, and these two the same. Whereas if I go through the 4P, here you see there is a large ridge of coincidences. What is interesting now in this? What is this going to tell us about the states which are involved in this transition? Where if we project the intensity of coincidences versus along a line where the sum of E1 plus E2 is constant, which means more or less this diagonal line, and you work out the energy conservation, you can show that that's going to give you a sort of spectroscopy of the doubly ionized state that you are going to occupy in this event and this event. But we said that this final state should be the same because it's only the intermediate step, 3D and 4P, that's going to be different in this case. So let's compare the two. In red, we have what happens with the 3P. And this is the line, these are the states, and these are assigned as holes in 4D in 2 different sites. This multiplied here is exactly what you expect for 4D minus 2 configuration. And then here you have satellites. Now, if we, instead of going through the 4P, the 3p, we go through the 4D, what you get is the blue line. So there is a reduced probability of finding 4D minus 2 configuration, whereas we have extra contributions here. This extra contribution is better seen if we get the difference between the two curves, and we highlight this peak P1 and P2, and these are two manifolds of excited state of the system that are accessed only when I am ionizing through the through the 4p electrons. Why? Because the 4p ion, the 4p hole is not a clean hole, but it's a resonant state between 4p minus 1 and 4d minus 2 for half, and this is going to give access to highly excited state whose lifetime is of the order of the lifetime of the core hole that I have created. So it means I am building a spectroscopy of excited state which leaves sub-femtosecond periods. And so it means that we can perform by this experiment a spectroscopy of very short-lived states that is nowadays accessible through, for instance, pump and probe experiments. But instead of having to rely on ultra-short light sources, we can just rely on continuum sources and analyzing on the energy scale. So to get this time resolution through the energy scale rather than through the duration of the pulse. In conclusion, what I can say is that this one photon in, two electrons out experiments allow a sort of exchange correlation imaging. So we have seen that we can see either as a core hole starting from the size of a Coulomb exchange hole and down to the lifetime of the excited state due to correlation. And they give us a direct verification of the principal model used in describing correlation. And these are existence and extension of exchange core hole, strength of the exchange and correlation interaction, spin dependence of exchange correlation in magnetic materials, dynamical screening effects in the scale of tenths of attosecond. There is a drawback. So far, the experiment yield is too low to propose the spectroscopies as routine spectroscopies. However, over the past 30 years, the progresses that have been done both in synchrotron radiation sources and in parallel detection have allowed to reduce the integration time for this experiment from weeks to few hours. Finally, the upcoming of ultraviolet and soft X-ray laser, it will make it possible in the future to carry out these experiments in academic, not only in synchrotron radiation sources or even in industrial laboratories. So we might foresee for this some kind of future development as it has already happened for photoemission. So with this, I will leave you with the take-home message, which is never underestimate correlations. And I thank you for your attention. And now I'm here to answer your questions.
Thank you, Professor Giovanni. Now, if you have any query, please raise your hand so that we can ask the question to speaker. Yes, Didier.
Yes, Jenny, thanks for this beautiful talk. I have a small question. You in one of your last slides, you showed that a small peak that you associate to a plasma. I remember from talks and spectra that you showed me, and that Wolfgang Werner showed me that in E2E it's quite easy and customary to be able to track a plasma. But in gamma 2E, what about gamma 2E? Is it easy to identify plasma?
Good question. Very good question. I never gave a real thought to this, but to identify, I mean, it is easy it's easy to identify a plasmon if we stay in the two-step model. Say, if I can relay on a long-lived core hole state, then the photoemission spectrum, it's mostly dominated by single particle behavior. So I can easily discriminate, say, a main peak from a plasmon satellite. And in that case, I can tune the photoelectron on the plasmon satellite and then look at the Auger decay, which are following the excitation of that plasmon satellite. Actually, this is something that we have in mind of doing since long. We have done something like this in the lab, but the light was not polarized. We had no angular resolution, and so it just showed that it is feasible, the experiment, but nothing more. Whereas if the lifetime of the core hole is short, then what happens is that this becomes a double photoemission resonant through a core hole state. So the core hole state energy becomes ill-defined. And so how can I distinguish an event in which the plasmon was excited from the one in which it was not? This is not clear to me. But I would, right now, top of my head, I would say it becomes impossible, but I would like to better think of this.
Okay, thanks.
Welcome.
Yes, Amol.
Thank you, Professor Stefani, for such a wonderful talk. I have just a couple of queries.
Sorry, I can't hear.
Yes, you are audible.
Yeah, I have just a couple of queries. Hello.
Yes, I can hear you.
Okay. So actually, I wanted to ask, like, what is the typical time delay between a state going from A to A plus and then A plus to A double plus? So what's the basic delay between these two events?
Okay. The delay time is the core hole lifetime. So is something, it depends very much on how deep is your hole. But say we are in the order of picoseconds or less. So for what concern discriminating the coincidences, the resolution in time that we are able to perform nowadays is in the order of, say, 0.1, 0.05 nanoseconds, no better than that. So actually, from the point of experimental detectability, those are events happening at the same time. So I can discriminate a long-lived, I repeat, I can discriminate long-lived by short-lived only on the basis of the width in energy of the spectra that I measure. The uncertainty principle will tell me that the shorter the lifetime, the broader the energy spectrum.
Okay. So here actually we are using this frozen orbital approximation for this theoretical understanding. Like during that time, the other orbital of the electron is frozen.
Oh, okay. I believe that the frozen orbital approximation starts to give you problems also when you have long-lived core hole states, because it means the frozen core approximation means that to the zero order you are forgetting about correlation between the electrons. You make a hole in one orbital and all the others don't recognize it, which is simply not true. But you see the limit for this already in the conventional photoemission spectra. Because in a conventional photoemission spectra, you shouldn't have any satellite if you were strictly applying the frozen core approximation. Isn't that true?
Yeah. And yeah, one more thing, like when we want to disentangle this correlation effects. So in one of your slide, you have mentioned like 4 or 5 analyzers you have kept. Okay. So is it possible to perform similar kind of experiments, this kind of analysis using this Stern-Gerlach type of apparatus, where you put a magnetic field and see how the parallel spins and anti-parallel spin part go with?
Yeah, I think you have got exactly the point. They're trying to pinpoint where correlation become. If I was to measure just the conventional photoemission spectrum, I would see playing at the same time in the spectrum all the orbitals of my target, right? Mm-hmm. And usually have large overlaps between, say, the multiplet coming from one orbital, the multiplet coming from another orbital, and so on and so forth. And so the information is rather fuzzy. With this coincidence, what I can do, and indeed it has been done in some experiment, for instance, you can fix one of the analyzers on a given Auger transition. So once you fix a given Auger transition, it means that photoelectrons can be coming only by the parent core hole state. And if at this point I measure the coincidence photoelectron spectrum, what I get is the pure photoelectron spectrum of your core hole state, which is not possible to be done just measuring a conventional photoelectron spectrum. Vice versa, if you fix the photoelectron, you get a pure Auger line shape that comes from exactly that given and specific core hole state. Yeah, that's exactly, you got the spirit of this kind of measurements.
Okay. Yeah, actually, recently there are some experiments where they are using this photo emissions to diagnose, as a diagnostic tool for ultra-intense lasers. Like it's very difficult to characterize the ultra-intense lasers, so they're using these photo emission techniques to kind of pinpoint what's the typical intensity of those lasers. So those
they have been using this technique very much, for instance, on molecules, to try to disentangle. If you are interested, Rakesh has my email address. You can send me your address. I will be pleased to send you references for application to molecules and atoms.
Oh. Thank you. Thank you.
Welcome.
Yes, anybody else?
Yes. Yes, Rakesh, I still have a question for Gianni.
Yeah,
Yes.
please.
Gianni, could you show again, please, while talking, Amol was talking about disentangling. Could you show again the formula of the Chini-Zawadzki model?
Yes.
Because I don't know about it, but there is something I would like to understand. Well, I can give my question in the meantime. As you well know, in photoemission, when you want to disentangle the contribution of different layers to a core level peak, it's quite involved. And this was my question. In the Chini-Zawadzki model, the intensity of the Chini-Zawadzki peaks, is it given by a formula, or is it a parameter that you have to play with when you do the disentangling?
Right. Okay. It's given by the formula. For instance,
It's given
in the case that is shown here, what we did, it was to get the original dose for iron and to auto self-convolute them, which is and what you get is this one.
Yes.
Then we have simply used this formula where U is a parameter, and what you get is this height. Or now, if you go and compare with the experiment, you don't have to expect that this height is reproduced. Also because, strictly speaking, this model will predict a delta function. And then this is forcedly broadened, right? But the position in energy, that's quite well reproduced. And as I show in the example of iron on silver, it's trustable enough to the level that you can build up a test function, a trial function for your experiment, in which we have this formula describing each individual contribution to the line shape and U as free parameters.
Okay.
And in the end, we were getting a very robust minimization of the chi-square.
And did you try, this is my next question, of course, because I mentioned the problem of the decomposition, which is well mastered, but the problem of the decomposition of a core level photoemission peak. Did you try to do it the same way, so to have flexible parameters that you can optimize and see if it was giving the same as the Chini-Zawadzki approach?
Sorry, I think I haven't quite got your question. Could you repeat, please?
Yes. So in photoemission, in the core level peak, when you want to without any prior knowledge or almost no prior knowledge of your position of your chemical shifts, you have a certain process where you optimize and decompose your core peak into several sub peaks corresponding to different different layers. If you do the same here, would you get something quite similar to the Chini-Zawadzki result? Because as you said, in the Chini-Zawadzki result, the position of the height of the peak is more or less fixed.
Okay, well, let's say, no, it's not this one that I want. Please, let me.
Yes.
Okay, here, for instance. Well, actually, what we have done, we have found also an old paper that was parametrizing the correlation energy just in a phenomenological way. It was saying that the distance between, say, as is shown here, this red peak and this maximum is the exchange correlation energy. So we have tried to interpret this spectrum using this phenomenological way and using independently the Chini-Savasky, and we came to the same result.
Okay. Okay. Yeah, that was my point, because when you look at, for instance, the upper spectrum, okay, you have a certain number of peaks from the Chini-Savasky, and if I reason from the photoemission point of view, actually you clearly see that you've got the features corresponding to these peaks on your overall spectrum. You've got the shoulders and dips and so on. So I guess that a similar approach as in photoemission would give quite similar, results that would be not too far away from the Chini-Savasky model.
You are perfectly right. I mean, at the zero order, I mean, if I was to reanalyze some kind of new experiment, I believe that I would start from the phenomenological analysis and then refine it through the Chini-Savasky model.
Okay.
Because,
okay, thanks.
Fitting procedure are always a little delicate, but in this case was not.
Yeah. Okay. Thank you, Jenny.
You're welcome.
Okay, one more question we can take and then.
Sure.
Okay, there is no more question from the audience side. Can I ask one question?
Please.
Okay, so how difficult will it be if you perform this experiment with electron beam? In the low momentum transfer, it will mimic like photoelectron. The E2E or E3 process will behave like photoelectron type process. So in that case, I know that it will be difficult task with the electron gun, with the triple coincidence.
In principle, you could get the same result, as you said, with an E3E experiment, in which you get a fast electron, you scatter a small angle, and so you get a pseudo photoemission, and then everything comes exactly equal. Problem is that usually with electron beams, especially on solids, you are killed by the background of the secondary electrons. And the more are the electrons that you have to detect, the more severe is the problem of background. But it might be conceivable to do this experiment on an atom or on a molecule, because then the background problem is much reduced. Actually, we many years ago we did something. It was not a truly three electron coincidences, but it was with the fast electron. We were not detecting we were detecting only the scattered electron. We were not detecting the ejected electron, but detecting the scattered electron and the Auger electron. We made the coincidences. Because at that point you can assume which was the energy of the ejected electron and roughly which was the direction. So I'm talking of an experiment I did together with Asdin Laman Bennani in Paris some, 35 years ago. But nowadays it could be much easier, but could be simpler, not easier. It could be simpler to perform the experiment with detecting the 3 electrons. So in that case, I would say definitely C. Yes, it would be possible to make this experiment with electrons.
Okay. So there will be no more questions from the audience side. So I would like to thank Professor Giovanni Stefani for giving this talk. It was a wonderful talk, and we all are benefited by this talk. And thanks again. Would you like to say something?
I thank you for giving me this opportunity, and I wish we could very soon repeat something like this in presence all together. Okay?
Yes. So with this, I formally close this session and we can disperse. Thank you very much.
Thank you again.
And happy Easter for you.
Happy Easter, everybody. Sure. Thanks.
Yeah, happy Easter to all of you.
Okay, thank you.
Hi, Didier. We talk next week.